Hi there, welcome back to the channel. Welcome to another project, which is actually a continuation of a previous project. This is the loop antenna version of the low power AM transmitter that I presented in the previous video. And this is the one that really impressed me. I mean, it's very fiddly. It took a lot to get it really perfect, but hey, I got it as perfect as I think it's going to get. And I'm really chuffed with this thing. This one is working so much better than I expected. It has restored my faith in AM transmitters, in the medium wave band, the broadcast band, which I was a little bit skeptical about. You know, I'm a fanatic for Bluetooth and FM, but this thing really got me excited. And I think my radios in the house are going to get a lot more use out of this, because the result is it's a very portable little transmitter, very directional as well. It allows for adjustment of the modulation level. It allows for the adjustment of the tone that you want. So if you want more bass, you can get more bass, less bass, you can get less bass. Very simply done. It allows for the antenna tuning to optimize the actual strength of the signal going out. It allows you to adjust the frequency across a certain band in the medium wave band. And I've even developed a little RF meter that just plugs into my multimeter and works very well as well. So this thing sort of snowballed into a whole lot of learning experiences, and I had a lot to learn. And if you do too, or you just want to see me go through my experience, stick around, enjoy the video. And here she is, the complete project. And there are a few superfluous sections on here, which I'll describe in a minute, because it does look rather bulky. But to start off, let me tell you that the bottom section, this whole section here, is a battery pack, which I will show you in a minute. That's the battery pack, that's the transmitter, that is just the antenna. All the controls we have here are on-off switch for the battery pack, which really wasn't necessary, but I decided to put it in anyway. It's 24 volts out, and I can charge it with 25.2 volts, 0.5 amp current limit. This is 18650 cells. I will open it up and show you in a second, although this is not an integral part of the project. You could power this thing with a wall wart as long as it's a very good one. And then we've got the actual transmitter over here in the middle. It's got one control accessible to the top, and that is the frequency. And then we've got an on-off switch and a LED just to show us that it's powered up. And then we've got the antenna with a tuning section. So it's got a tuning condenser in there, so you can adjust the tuning of the antenna. At the back, all we've got is the power in from the battery pack or from the wall wart, 24 volts. Remember, this is the unfair version, so it works on 24 volts. It obviously works on a lot less as well. I've tried it, but the circuit is designed to be optimum at 24. And then I've got the two antenna out points over here. This is the actual signal. This is ground. This goes to the loop, signal, ground, and that's it. It's pretty clean. It is completely autonomous when I use it with the battery pack. And that's the idea, because this thing is directional. So with the battery pack, I don't have to worry about which direction I want to place it in. It moves around quite easily. But let me go into detail and describe each of these sections. This battery pack I designed because I wanted to use this thing on battery power. It is a lot cleaner, and I did not want the mains hum issues to become a problem, and they can be. So I produced this, which is a 24 volt, well actually it's 25.2 maximum battery pack. And at the moment, it's made up of two sets of three 18650 cells. They're in series. Remember, these things when fully charged are 4.2 volts, so 12.6 in total. The nominal voltage is 3.7, so 11.1 in total. There's a 3S battery management system over here, and another one on this pack over here. At the moment, I have on order a 6S charging pack or charging BMS system. So the idea is to redo this, take these two out and put one in here that would manage the charging of the 6 batteries. And then I could really charge it with the 4.2 times 6, 25.2 volts from my bench supply. And I give it a 1 amp or half an amp current limit. In fact, I think I've said here 0.5 amps. It charges at 0.5 amps constant. And then when the charge current is less than 0.5 amps, it starts doing constant voltage. This is how you're supposed to charge 18650 cells. At the moment, I can't really charge this because, well, I can. I have to separate this and charge this pack with 12.6 till it's fully charged, this one at 12.6 till it's fully charged, and then wire them up in series. So don't forget, these things are here temporarily, but the pack is nice and neat and clean. There is an on-off switch over here with an LED. This is the power out, and it's also the charge in. So it's the result of the two packs in series. And as I said there, it's nominal. I call it 24 volts. It can be anywhere from about 22 to 25.2, but that's the idea of this arrangement. So that's out of the way. And as I said, this is just the power pack, and you can use a different supply, a normal bench supply or a wall wart. The idea of using this pack is that it becomes very mobile. The whole system becomes untethered from the wall, from a socket, from anything like that. And I like this idea. I've also made this the same size as that section there, which is the transmitter, so that you can literally place them on top of each other. In fact, if you wanted to go further, you could stick them together with something permanent or temporary, but that's something that's up to personal preference. So let me put this aside and show you the other two parts. I'm going to separate them, get rid of the supply and undo these guys. I do see the irony of this being more a 3D print project than an electronics project, but there you go. Let's get the loop described next. You can really make this loop out of anything, but I decided to 3D print it simply because I can. And it's a 30 centimeter diameter loop with provision for 2 turns. And this is what it looks like. It's a little bit finicky to do because I wanted to make these grooves in here to allow it to hold the wire properly. I also cut it in 3 sections when I finished because I needed to print it and my printer bed would not take a 30 centimeter diameter loop. And this is actually slightly more than 30 centimeters because I've used the 30 centimeters as the diameter of the part of the loop on which the wire actually rests. So 30 centimeters diameter, and I broke it up in 3. As you can see here, these are 3 bodies, and I can show you what that groove looks like by hiding one of these bodies. You see what I mean? I've made these grooves in here. The diameter of this is the diameter of the wire that I'm using, which is actually 1.5 millimeter diameter wire in its insulation. So it comes to about 3 point something. It's actually called 2.5 millimeter square wire for household use, solid copper wire, about 7 millimeters apart here. What you see here is actually a little cutout, which is a negative. And on the other body, the other section of the loop that I cut out, there's a positive. So they clip into each other. You can put a bit of super glue or whatever. And even if you don't glue it, the actual tension that the wire is putting on there will hold the loop together. But that's really all it is. And down here is where the wires will start, go around, come out here, go across that way, go around, come out here. This is where the wire comes out. And this section will fit into the base that I'll show you now. And this is it. But I'm not going to go into detail on this base here because I redid it and I'll show you the improved version. This is the base that I'm using. I made it a lot simpler. The bottom of that loop just fits into this cavity over here. It hits that ledge so it stays in place. You can, if you like, use a bit of glue to make sure it stays together, but the fit is pretty tight, so I didn't need to do that. This is these 2 holes are for the antenna bolts, the ground and antenna. And this one over here is the hole for the tuning condenser knob, which I've also designed over here. And because I've used one of those little condensers, little tuning condensers that you get on FM radios, they need to be put against something. There's no thread to thread it through the hole. I made this section come out a bit, and I made that one as well, just to keep them the same. It's got feet protruding a little bit. My idea was to fit this into grooves that I would have on the lid of the actual transmitter, but I didn't like the idea of making the lid so thick that it needed to be very thick to accommodate these holes in there. So I decided not to use that. What you can do is just put a couple of rubber feet on there, or 4 rubber feet on there, so it actually grips a little bit better on any surface. That is the loop. And this is what it looks like close up. We've got the 2 wires coming in here from the loop itself. And I've got them going straight to the bolts for the antenna. And I've got the tuning condenser, the little tuning condenser from one of the really cheap FM AM radios. I've got all the sections in here paralleled to give me as great a range as possible. This one goes from 16 picofarads at its lowest, which is when you turn clockwise to a peak or a max of 300 picofarads when it's counterclockwise, because all of them are paralleled, and so you've got ground, or you've got one section going to there and one going to there. This is directly in parallel with the loop. So there's no real mystery here at all. Let's continue. Okay, remember this thing is a continuation of the previous version, which was the one that uses one 3-meter wire as the antenna. So a lot of this is identical to the previous version. The board is the same board, and I'm going to tell you what's the same and tell you where the differences are. So let's look at this more closely. Just like in the previous one, I use one of these Bluetooth modules. It's receiving the signal. It's getting powered from the 24 volts through that 5-volt regulator. The differential between the output voltage, 5 volts and 24 coming in, is a lot higher, but the current is so small, this thing just gets barely warm. If this thing drew more current, I would have to put a heatsink on there, but as it is, it's not an issue. So that powers that. This thing produces the audio signal that it's receiving through those two resistors, makes them mono, and it comes down to this capacitor, which then couples it to the modulating transistor over here. The circuit makes that a lot easier to understand. Here we are, the loop version. Very, very similar to the previous schematic, but there are indeed a few subtle changes. Let's go through them quickly. 24 volts comes in. It's now called the 24 volt line. This resistor, I think I've actually changed to 22K. Yep. So 22K through the LED, power indicator. Okay. 24 volts comes in. I put a 1 millihenry inductor there just to try and reduce some noise. This is exactly the same as it was before. I've got 5 volts coming out. That is the output to the Bluetooth module. It's going to power the Bluetooth module, and the Bluetooth module then brings back the audio, left, right, and ground signal from the audio that it's receiving and decoding. And here it is, left, right, and ground. These two get summed to create a mono signal. This capacitor allows the full frequency band, or the frequency range of audio coming in here, to modulate that transistor, or to modulate the bias of this transistor and therefore modulate the carrier. However, if you have too much bass, if you find that your signal is too boomy, bassy, whatever you want to call it, what you can do is make this smaller. And in fact, what I've done is I've tried 0.1 microfarad and then 0.33 microfarad. And I'll show you why that's important in a second. I've made this adjustable. It's not a tuning condenser. What I've done is I've just used 2 sockets as the pins, and I can then just plug in whichever capacitor I find is perfect for that purpose. I tried 0.1, the signal sounded a little bit too tinny, so I tried 0.22, better, and then I tried 0.33, and that was the Goldilocks one. It sounded brilliant. The bass was good, but it wasn't overdriving the modulation, so it wasn't blabby, saggy, whatever you want to call it. So that comes in. The only difference here is that the bias is different. Because I want the same 2.6 volts over here to create 2 volts over there, and therefore create the bias current, or the current that this current source is pulling down and then in turn modulating. I've got to make this resistor higher, and this, because of the 24 volts. So this becomes 3.3 and 24 volts. That works. What else is there? That stays exactly the same. That's all the same. This part here, again, same story, but these resistors are slightly different because we're using the 24 volts supply, and we want the same bias voltage of about 6 volts over here. So this resistor combination is slightly different to the previous one. They're exactly in the same place on the board, so no problem. Same on this one over here. And then we come to the antenna part, and this is where things really change. The coil, that toroid auto transformer thing that was here, that disappears. It's replaced with a 100 microhenry inductor, for which provision has been made on the board already, had been. And it then comes out here and it meets these 2 capacitors. And then there's a trimmer cap across the end. Now this has changed, and I probably should show it on here. This thing is actually 16 to 300. Now, what can you do here? Well, you can actually use a very small trimmer if you put a fixed capacitor on here. So let's say you've got a 22 picofarad trimmer and you make this 220 picofarads. That means that you can go from 220 to 240 or something. I prefer to use this because it's a lot more, it's easier to find the range, and it's worked for me, okay? It's up to you. I think that this capacitor that I'm using is fairly leaky, meaning that the Q of the circuit, which you don't want to be too sharp, but you also don't want it to be too wide. The Q is the, well, how do you work out the Q? It's the frequency at which this thing is resonant. Let's call it 1.3 megahertz. Let's say I'm transmitting, the whole thing has been set over here to 1.3 megahertz. If I have a 13 kilohertz bandwidth from minus 3 dB to minus 3 dB across the resonant point, that means that the Q would be 1,300 divided by 13, okay? So the Q would be 100. What you want is to make sure that that bandwidth is less than 9 or 10 kilohertz. So you need to make sure that this Q is pretty sharp, but not as sharp as it usually would be. If you use perfect capacitors, very low resistance, very low and perfect inductors on here, you would get a Q that is so sharp that only your bass would go through. Only the low frequencies would go through, and you'd get no treble. So your audio would sound bloody awful. Mr. Wenzel says that for voice radio, you need a Q of about 225. You need a higher Q even for music. How high? Well, if you take 10 kilohertz divided by 1.3 megahertz divided by 10 kilohertz, you need a Q of 130, right? You need a Q of 130 to fill that 10 kilohertz range perfectly. That's neither here nor there. I'm actually getting more than that, which is not a good thing if you want to stay within the legal framework of an area, in an area that has a lot of transmitters. In my case, Madeira 1 AM band transmitter, I don't think I've got an issue. And this thing is very low power anyway, okay? So because you're transmitting 10 or 100 milliwatts, but the efficiency of this type of antenna is so small, I don't believe it should be a problem. Okay, this resistor here is just provision on the board in case you want to drop the Q, which, as I said, I've not had to do. Okay, that explains all the schematic part of it. Now, the big problem for me was finding the right combination or the right capacitors for this one and that one. I tried all sorts of things. I tried smaller ones to fit them nicely on the board. If you remember, the board had provision for 2 smaller caps. I wanted to use the smaller film caps. I tried them in here, same value, 8.2 nanofarads, and it just wasn't giving me a good signal on the output. You'll see just how good these two work. These are 2 film caps. They are 8.2 nanofarads. They're a little bit bigger than the board was made for, but hey, there's so much space in here. I'm not gonna have a problem with that. This little trim pot is the same story as before. You can adjust it to give you 100% modulation or close to 100% modulation when your iPhone, your phone that's sending the signal via Bluetooth, whatever source of Bluetooth you're using or transmitter, you set the volume on that to max, and you can adjust this to give you just less than 100% modulation at full volume. It prevents you having distortion going in when you play the volume of the device you're sending the audio from. Now, enough talking. I want to show you this thing on the scope. This thing is bloody amazing. This thing's giving me incredible results. And I'm so happy with it. I don't think I'm going to have version 3. I hope not. But I'm not going to swear that I won't because I know myself. But let me show you just quickly what that capacitor story was. See that there? That capacitor is removable. Try and remove it. You see, there's 2 little sockets on there. And I can now just plug this cap. Whoa. I can plug the capacitor in. And I'll do that off camera because I've got to pick it up. And I can make that capacitor smaller or larger depending on what kind of body I want my audio to have. As it is there, it's 330 nanofarads. If I want more bass, I can go up. If I go up to 10 microfarads, which the circuit calls for, it allows the full audio band to go through, okay? If I go down to 100 nanofarads, I'm cutting off a lot of the bass, so I'm probably going to get this thing getting a bit tinny, which you don't really want. But the one I found that is perfect is 330 nanofarads for me, for my ears, for my receivers. And again, that's just personal preference. But again, enough talking. Let me show you the scope, show you what we get here, and show you the effect of adjusting that for the modulation level, adjusting the frequency, and also adjusting the tuning of the antenna. Okay, we've got it all set. I've got the loop antenna connected with very short wires. You've got to make this short because you're going to increase the inductance, and that unbalances the loop. So this thing can only be tuned, the antenna can only really be tuned when you've got this thing completely settled in place, the way you're going to use it. What else do we have? I've got the scope measuring the output signal. So I've got the scope ground to the ground lead and the scope itself to the loop output. And I've got the Bluetooth module blinking away because I haven't connected a audio source yet. But let me show you what we are seeing just like that. As I switched it on, I left it for a few minutes just to get the oscillator to settle. It does take a few minutes. So let me start the screen recording for the scope signal. And that is what we are seeing. We are seeing, what is that, 1.38 megahertz. I've got 11.0 volts peak to peak carrier. That's a beautiful carrier. Now let's first peak the antenna. I've got this on minimum capacitance. So if I go up, there we go, I'll reach the peak. Now this you may have to play with. Actually, let me tell you, you're going to play with a lot of stuff. Don't think you're going to build this straight off and it'll peak perfectly. You've got to play with different capacitors. You've got to play with different lengths of wire. You've got to make sure that you don't have excessive length of wire between the output and the loop itself, because that changes the inductance. The inductance is an integral part of the tank circuit on the output. So everything is connected here, okay? So that is a peak power or peak voltage swing. And what am I getting? 17.4 volts. This is unmodulated, okay? This is an unmodulated carrier, and I can change the frequency. I'm not sure what the range is now. I think I've got it at the maximum. Let's see. Actually, the best way to see the frequency adjusting is to do that, because you can see it sort of move away. Let me try again. 1.37. And of course it's going down because the antenna is no longer peaked at that frequency. But let's do that. I can't remember what the range is on this anymore because I changed I've got a 47 picofarad capacitor in there, 0 NPO capacitor. I'm trying to go closer to the screen. 1.29, 1.27, 1.24. That's too small. Actually, let me just change I can adjust it slightly there. So 1.21 is the minimum. And if I go the other way, and of course I'm going to go across the antenna section, it's 1.37. And it's going down again. 1.38, I think it was. About 1.37. So, 150, 160 kilohertz, I think it is. Anyway, that's neither here nor there. You can adjust that as you want. And let's peak this again, because I have changed the frequency somewhat. In fact, what I do is I put what I prefer to do is I prefer to put this at about halfway, which is about there. And then I can actually peak it by adjusting the frequency. Now, provided I don't have any stations on that frequency, I can do that. And as I said, the one good thing about not having many stations in Madeira is I'm free to play with the band. There's my peak, 17.4 volts, and it is at 1.3706. And that's what we are looking at the output without modulation. Okay, so let me get a modulating signal. Let me get my iPad, send a tone on here. I've got a signal generator app on the iPad. Send a tone on here, and we'll see what the modulation looks like. I just had a rather unpleasant surprise. I switched everything on. I connected my iPad to the Bluetooth. As you can see, it is connected. The Bluetooth LED is now fixed, constantly on, and I got nothing. I couldn't get the modulation. And then I finally realized I'd forgotten to replace this little capacitor. So remember, this thing fell off and I said I'd put it back later. It was lying on its side there. I put that in, and this is what happens now when I put the volume up on my iPad. It's going up, and you can see the modulation, okay? Now, the best way to see the modulation is, in fact, to do that, but we have triggering issues, always do. It's not bad. So let me increase the amplitude to max. It's now on max on my iPad. Try and get this thing to settle down. Let us peak the signal. Geez, this triggering is an issue. I'm sure there's a way to do that. I just don't know how to do it any better. There we go. So that is pretty much 100% modulation. Now, if I go to here, to this trim pot, that's a 1 kilohertz tone I'm sending. Yep. And I think I'm going to set this to trigger with the AC line so that it still moves, but not as badly. But you can see that it's changed, and this is less modulation. You can see the dips getting less pronounced, and if I go up, I can actually go over 100% modulation. That's too much. So let me get it to where it's perfect. There we go. Now, if I drop the volume on the iPad, see that? That is a beautifully modulated carrier. Probably very close to 100% modulation. I like it. And I can still obviously peak this. At the moment, I'm probably at, let's see, where am I? 33.4 volts, peak to peak. This thing's producing the peak to peak on that modulated carrier on that modulated signal is 33.4 volts. See that? Now, this thing is still connected to ground, okay? Or to mains earth through the oscilloscope ground. I didn't like that idea. I didn't want that. So I decided to build a little RF probe or RF meter detector. And I looked at all sorts of options, and then I find out that there's one where you don't need to do much at all. In fact, what you can do, actually, let me show you, because I think this is really neat. Somewhere on the web, I found the simplest of RF meters, and all it is signal comes in at the antenna, goes through two 1N34A diodes to the respective outputs here. Across there's a, 1 meg resistor and a 10 nanofarad capacitor. And this is what it's doing is it's actually taking the RF signal and it's rectifying it and then passing it to two outputs. And those two outputs I use as pins or plugs for the multimeter across there. And this has been sort of heat molded into this little case. It's the right distance apart. You put it on millivolts. And now when I go to, let's put it in line with the axis. It's now in line with the axis or close. You see that? I can actually see the directionality of this. Let me put this up here. I've got to make this swivel a bit more on two planes, but 39 millivolts. It's on the millivolt range, DC volts. There's my peak going straight, well, remember the antenna's over here, and I can move it away. I'm just showing you a rather extreme example. Peaking it there, and it starts getting lower, okay? Now remember I told you that this thing was directional in the line, in one particular direction. In this case, I've actually flipped the ground and signal to there. So that will be the highest direction at the moment. It's going in that direction. But if I put this on the other side of that loop, let's see what happens. See that? It's half. My hand obviously has an effect, but more or less in the same distance, it's half the strength that we were measuring on that side, half the number of millivolts that we're measuring on that side. So what you can do is just use something like this when you want to peak your antenna. Let me put it back to the other side. And it really doesn't matter what I read. I can, as long as I'm fixed, as long as I keep this still, and I'm actually going to show you the scope at the same time. Look at that thing there. I'm going to look at this and peak it there, but I've got to keep it still. I can't move this around, okay? So I'm going to keep it still. I'm just going to turn the antenna. It's gone through a peak. There seems to be the peak. It's going down. So the peak was there. There. And look at the scope. That is indeed a peak. Watch. If I go down, and I go the other way again, go down, and if I focus on the meter, there's my peak. Now look at the scope. It's doing the same thing. It's peaking exactly in the same spot. So I can use something like this without the scope. Now if I take the scope off, you see how much lower that is? Doesn't matter. Let me just stand still or keep it still, and I can still peak it. I know that that's my peak. So I don't need to connect the scope to ensure that I've got the best signal. I could use a radio nearby and listen to it, but this is perfect because all I need to do is plug this, connect that to millivolts. I've got this thing, got a little cover on it. Connect that to millivolts, put it nearby as long as I'm getting a reading, do the peaking, and that's it. And because you're not going to be changing frequencies a lot of the time, you just adjust it to a frequency you want, put that meter nearby, do the peaking, and that's it. You've done. I like it. I like the simplicity of that idea. I'm going to do a quick test just with these two radios. I'm in the living room, so let's push play on the... I've just pushed play on the iPad. Let's just pause. I've paused the iPad. The listening level is fairly high. I'm just getting a very, very slight hiss, which would be normal anyway. But remember, this is directional. So least hiss would be here. Push play. Too loud. So that's on that one. This one, my favorite. Let me try pause again. This one is directional. Put the volume up. Now this is in the lounge with TV going, equipment all over the place. Sounds bloody brilliant. I can drop the volume on the iPad, which means I'd need to put the volume up here, but then I get more signal to noise or less signal to noise ratio. It's always best to modulate as high as you can get away with. I like it. I like it a lot. Try something else. This thing sounds really, really good. There is something making noise in the background here somewhere. It's the TV set. Well, can't get away from that. Okay, this is looking promising. Actually, it's looking much more than promising. It's looking really, really good. I think I've got myself my definitive AM transmitter for the broadcast band for medium wave. I like it. I really do. I listened to it last night. I put it on for some time because I wanted to see if I got any listening fatigue. That tends to be a problem with some of these medium wave broadcasts. No, I don't. So the band of frequencies that's getting through is good. It's making the sound good. And of course, I've been trying music. I haven't tried talk radio or talk, podcasts or something like that, which should even be less demanding of the fidelity. I really, really am pleased with this. And as a result of this project, I learned an enormous amount, mostly, obviously, from Mr. Wenzel's description of the schematic of this circuit. That was what really started this whole project. The first version, the second version, he's got some other ideas there. I definitely recommend you go and visit his website. It's linked down below. The other references I used are also linked down below. And also down below will be the files for the 3D prints that I've done on here. If you want to repeat them, if you want to do them yourself, go ahead. It's in the Google Drive folder that I link below as well. Please do not ask me to do it for you. I don't have time for that. This is just my hobby. And if you want to play with this, be ready to or be prepared to do a lot of experimentation. That is part of the fun for me. If it's not for you, buy yourself a commercial transmitter. It's probably an easier solution than doing this. This does take a lot of fiddling. That's part of the fun for me. And of course, the PCBs used on here are also in the shared section of the PCBWay website. So by all means, go there and order them yourself or download the Gerbers and do them yourself. I really don't mind how you go ahead with this, just as long as you really get into it and enjoy it. I do hope you have enjoyed this. And if you have, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon and PayPal. Links are in the description below. Once again, thanks for watching. Bye for now. And most of all, stay sane.